It's a great pleasure to introduce our speaker today, Ivan Veselic from TU Dortmund, who will tell us about quantitative unique continuation estimates and uncertainty relations for Schroedinger and divergence type operators. Please, Ivan.
Okay, Kirill, thanks a lot for the introduction. So I will be talking about several projects and several papers, and you see that there are many people involved. One of them is Michela Egidi, one is Ivica Nakic, one is Matthias Teuffer, and then Martin Tautenhahn. And then I contributed from time to time also something myself. So the topics of the talk, they concern quantitative unique continuation estimates. So these are results from the realm of partial differential equations, which then translate into uncertainty relations, which are more known, let's say, in mathematical physics, quantum physics. You have heard about the Heisenberg uncertainty relation, or maybe the Hardy inequality. And also it features in Fourier analysis if you think of the Pay-Leviner theorem. Now, I don't want to start with abstract things with some uncertainty relation, because then you don't have a feeling what this is good for. So I will start with one of the applications, namely with controllability of the heat equation. And then you will see where quantitative unique continuation or uncertainty relation enters into the business. Okay, so we have a domain, omega, which is a subset of RD, open, and we want to study the heat equation on this domain, more precisely an inhomogeneous heat equation. And there will be a special subset, a measurable subset S of omega, which should be non-empty, which will play a special role. And we consider the time evolution from 0 to a positive time, capital T. So you see the inhomogeneous heat equation, which is written here, and it's defined on omega and in the time interval from 0 to t. So the driving operator, the generator, is just a Laplacian. There's nothing else involved. And we impose some nice boundary conditions, for example, Dirichlet boundary conditions. We want to use some operator theory, so we want self-adjointness. We could also impose Neumann boundary conditions, but it's fine if you think of Dirichlet boundary conditions. And then we have an initial value of the function w, so this is w naught. This should be functions in L2, in a Hilbert space, and we will be considering mild solutions of this Cauchy problem. Okay, so now I mentioned that there's this measurable subset S of omega, which plays a role. And actually, we will be considering only inhomogeneities U, which are supported in S with respect to the space variable X. In the time, they will be supported in the full time interval. So it is well known by, well, maybe some simple semigroup theory that the Cauchy problem has a unique mild solution, and you can describe it by some type of Duhamel formula, which we will see shortly. So this direct problem has a unique solution. By direct, I mean you prescribed an initial value, you prescribe in inhomogeneity, and then you find a solution. What will be of interest in the following will be an inverse problem, where you actually don't prescribe in inhomogeneity, but rather you will like to find inhomogeneity U satisfying certain properties what you are interested in. So the inhomogeneity U is the unknown. Okay, so now you see the same system as you saw it before. So this is equation 1. The only thing what I've made now more explicit is this indicator function of S, which tells you that U is supported with respect to the space variable in S. So because whatever maybe the support of U outside of S, it just gets cut out in the formulation which I have chosen. And we say that this system is null controllable at time t if for every initial state W0, you can find an inhomogeneity U, which depends on the initial state, which is a function of time and space variable, and which is supported in space only in S, such that if you let W evolve with time until time capital T, you will drive the solution to 0. So it's possible to drive the solution to 0 in the time interval from 0 to t. Okay. There may be several such functions U. So it's there could be multiple solutions to this, but actually it's in some sense possible to find optimal solutions and actually show that there's a linear mapping behind it. But before we go into this, just let us fix some definitions, some nomenclature. If the system above is null controllable, then we will call the subset S an effective control set. This means that just by doing and controlling something on the subset S, it is actually possible to drive the system to a desired state. By linearity, it's quite sufficient to consider 0 to be the target state, and then if this is true, you can extend controllability also to a natural linear subspace, but I will not discuss this here. So if this is true, that we have null controllability or an effective control set, then actually the closed graph theorem tells us that the control cost is finite. You can think of this control cost as the norm of the inverse operator, which gives you for any initial state the desired control function U. Okay, but you can also define it in closed form, which tells you, which is the following: Ct, this control cost, is equal to the supremum over all normalized initial states of U, which is the inhomogeneity, which is of the norm, sorry, the infimum of the norm of U, where U is chosen among all the possible inhomogeneities which drive the solution to 0 of system 1 after time t. Okay, and that this supremum is actually bounded is related to the closed graph theorem if we are in the setting of null controllability, and this is, as I said, associated to a linear solution operator, which can be described by a variational principle, but it cannot be written down explicitly, this solution operator. Okay, so we have now explained what does it mean that the system is null controllable, and we have explained when we call a subset an effective control set. Now, these are all qualitative statements. These are yes or no statements. But if you have identified a system and an effective control set S, then you would like to give some bounds on the control cost. So how expensive is it to drive your system into a desired state, or in this case, to 0? Now, before we discuss this quantitative estimate, we turn back to qualitative results and want to discuss what are known geometric conditions to have an effective control set. And first, we consider the situation of bounded domains omega. So what was well known for a while, I guess by results of Lyons and Lebeau, is that if you have a bounded domain, then any open non-void set S, subset S, is an effective control set. more recently, starting 5 years ago, 6 years ago, it has been proven that actually you can remove the assumption of openness. You don't have to have a ball contained in the set. It's just enough if you have a measurable subset which has positive measure. And this is enough to have a effective control set and to drive it away. Sorry, to be able to control your heat equation. Now, if you consider an unbounded domain, omega equals 2RD, for example, this is obviously not true. Well, at least intuitively, it's clear that if you choose a small ball, you cannot heat from the small ball all of RD. If you don't believe it, you can make a small calculation in the following sense, that you choose an initial state which is concentrated on a compact set, and you have a control set which is a ball, and then you start pushing or shifting the support of the initial state further and further away from the control set, and you will see that your control cost will grow unboundedly, which is a contradiction to what we saw before. Okay, so now if you look at the both situations of bounded domains and of unbounded domains, we see that at first look, at least from the qualitative point of view, the criteria for null controllability on a bounded and an unbounded domain are totally different. So there's something new to understand if you have an unbounded domain. So that's what we keep in mind. But unbounded domains have been studied before, and let me first present a earlier known necessary condition for a set to be an effective control set in RD. It basically says that you need there must be some radius R such that the R neighborhood of the control set is all of the space. Okay. In other words, you can say for any x in RD, the ball of radius R around x has non-zero intersection with S. Okay. So this is a sufficient condition to have an effective control set. It was certainly pointed out in a paper by Le Rousseau and Moyano, 2016, and probably this is also the first one, but I'm not an expert in this literature. And one way how to formulate this geometric condition is written down in the picture below. If this condition which we just formulated holds, then it's possible to find two real parameters, positive parameters, G and delta, such that the set is G delta equidistributed. So this is a definition which will play a role in the whole rest of the paper, so you better remember it. So it means that basically this condition which you see in the picture below holds true. You create a grid of spacing G, and then you have certain cells, certain cubes of side length G, which are shifted along certain along a periodic lattice. And then with each of these periodicity cells, you have to find a ball of radius delta around a certain center. The center is not so important. The main point is that it's contained in this periodicity cell, and it should be also contained in S. Okay, so S should contain all these gray balls which you see in the picture. Okay, so this means that this set S does not just contain one open set or one open ball, but a lot of open balls, and they are equidistributed. Okay, so this is a sufficient condition, but it was not sharp. And last year, or well, before last year, I mean, there was some work in the years coming up, and in 2018 and 2019, two different groups, one of them with my participation, showed the following sharp criterion. So if you consider the heat equation on RD and you fix a positive time T, then the system 1, which I have rewritten here, is non-controllable in time t if and only if the set S satisfies a geometric property which is called thickness, and which we will formulate now. So a set S is called thick, or more precisely AR thick, if the following holds. So A is a vector of positive numbers, and you should think of it as a window, and each A1, A2 until AD gives you the size or the dimension of the window in a certain specific direction, and the window is denoted by QA. So this is something like a rectangle. Okay. And if you shift this rectangle around in RD by the base point X, and wherever you shift it, you intersect it with S, and you evaluate the Lebesgue measure, and this should be lower bounded by rho. This is the density times the size of the volume of the window. If this holds, then we call this set A rho thick. Okay. So rho plays the role of a density, and A is a certain scale or size, or it tells you whether this thickness holds also for a micro scale or for large scale, and so on. And we call a set simply thick if you will find some positive density and some window such that this property holds. Now, we know that if you have null controllability of the heat equation at all, then the set from which you are controlling needs to be A rho thick. And then it's very natural to analyze how the control cost depends on rho and A. This was done partly in the paper by Michaela and myself, but I will not spell it out here because we will see better estimates soon. Okay. So here you see a picture of a thick set in RD. The section, what you see, is of size 10 by 5. The window is 2 by 2, and the density is 1/8. Maybe you can do also better, but this is what I could calculate by hands easily, immediately. And so far we have seen two different notions, geometric notions of set, or geometric properties of sets, thick sets and equidistributed sets. So we want to relate them. Now one can see easily that every equidistributed set is thick, and you can do a small calculation. I have recalled here in the picture what the equidistributed set is, and you can do some calculation that if you have a G delta equidistributed set, then it's thick, and here are two possible choices of A and rho, such that you have an A rho thick set. I don't think that they are unique, because in thickness you have two different parameters to play with, and if you improve rho, maybe you can improve rho, so make it bigger, more positive, if you make also the window size bigger, or you can make the window size smaller and be more precise if you are willing to sacrifice a little bit of rho and make it smaller. Okay, anyway, we have a relation between these two notions of the sets, and obviously it has to be this way because our criterion for null controllability is sharp, and the previous condition was just sufficient. So it has to be implied by our condition. Okay. Now, before we start studying the control cost precisely, I want to embed this result in a more general abstract operator theoretic setting, which was pursued in a paper by Ivica Nakic, Matthias Teuffer, and Martin Tautnant, and myself. It will be quoted shortly, but just let us have the setting here. Again, we consider a control problem, but now we are not in a state space where we have some x variable, but we are in an abstract setting. We have an abstract Hilbert space. We have a self-adjoint operator A, which is lower bounded, and we have a bounded operator B. A will be something like negative Laplacian, and B will be something like the indicator function of the set S, which we saw before. So now we have U from L2 on the time interval from 0 to t with values in the Hilbert space X. And what we consider this Cauchy problem 2, which is just a generalization of the system 1 which we had before. This equation has a unique mild solution, W, which can be expressed in the following way. This is formula 3. You add two parts. One of them is the free evolution without an inhomogeneity, so it is just governed by the semi-group generated by A, and then you have an additional term which is expressed by some type of Duhamel formula, which we see then below. It's B of t, the operator B of t, acts on U in the way that you have a time interval from 0 to t, then you have the action of the semigroup, then you have the operator B, and then you apply it to the function U, which depends on S. Again, we say that the system 2 is null controllable in time t if for every initial state W0 from the Hilbert space, which is now abstract, you will find a null control function U, which depends on the initial state, which drives the inhomogeneous problem, the solution of the inhomogeneous problem, to 0 in time t. Okay. Again, you can define the control cost in time t as before. Here we have written it in a more compact way. So you have, this is the supremum over all normalized initial states, and then you take for each initial state the minimum over all good control functions. This means those control functions which drive your initial state to 0. So that's expressed in this form. Okay, and this control cost is something what we would like to bound later on. So before I state the theorem, let me just introduce some notation. We have a self-adjoint operator A, so you have a spectral calculus, and you have spectral projections and a spectral resolution, and a spectral projection from on that interval from -infinity to E, I will denote by PAE. Since A is lower bounded, although I have written -infinity, I could insert there some finite energy, because below this, the infimum of the spectrum, you will have no contribution to the spectral resolution. So there's -infinity written, but actually you're projecting on a compact energy interval. Okay, so we have the following statement about null controllability. And first, let us discuss the assumption, because it's complicated enough. And the assumption which we see here is some type of uncertainty relation. So we have three parameters, D0, D1, and gamma, which enter into the constant appearing in 4. Okay, but before we want to consider the quantitative dependence, the statement is that you have at all a constant, which tells us that you can compare two norms. One of them involves B star. B does not need to be self-adjoint, so B star appears. If B is self-adjoint, you can just write B. Now, B star could have a large kernel. If you have a function from a kernel, then the norm on the right-hand side will be 0. Okay, and then you probably cannot satisfy this condition. So what is written here is basically that if you take anything what is in the range of the spectral projection, you will not be in the kernel of B star. Okay, so they kind of have a skew geometry. So for functions in the range of the spectral projection, B star introduces a norm which is equivalent to the original norm, although you have maybe thrown away a certain subspace. Okay, but for this spectral subspace, this is still equivalent. But if you have equivalence of norms, you have a certain constant involved. And now these parameters enter, and you see that if E, the energy grows, this constant may become worse and worse and very fast on an exponential scale. And how fast is governed by D0, D1, and gamma. Okay, so this is a family of equivalent statements of norms, and how the constants behave in the equivalence and how they are allowed to grow is determined by D0, D1, and gamma. Okay, so if this is true, if 4 holds, then for this stated system, we have null controllability, or actually equivalently final state observability, which is formulated here. Okay, so for any time t and for initial state phi in the abstract Hilbert space, we see that the norm of the final state after time t is bounded by an observability constant, which will become explicit shortly, times the integral over time of the squared norm of what you see of the time evolution filtered through B star. Okay, so this is called observability estimate, and it's equivalent to null controllability. Now the main point is that we don't have just the qualitative statement, but we can explicitly say how the constants appearing in equation inequality 4 translate into the dependence of the observability constant, and then also in the control cost. Okay, I will not discuss all parameters here because this will be just too complicated, but I will discuss shortly some of them. But anyway, you see that the dependence is quite explicit, and these constants C1, C2, C3, and C4 are almost universal. They depend on gamma, but they do not depend on D0 and D1. Okay. Now, the system, as I said, the system 2 is null controllable if condition 4 holds, and the control cost is bounded above by this constant, which we have identified here as the observability constant. What you see here in formula 4 is called uncertainty relation, or specifically in the context of control theory, it's also called spectral inequality. Spectral inequality because PA is a spectral resolution, and so there are spectral data involved. So this is an abstract operator theoretic theorem. There have been similar results before, but not quite geared towards our applications in mind. So what can we do with this? First of all, let us discuss in a somewhat simpler case, or in an important special case, namely when gamma is set to be equal 1/2. Gamma was a parameter in the open interval from 0 to 1, so certainly 1/2 is a good choice. It's right in the middle. Okay, and if we insert gamma equal to 1, then the observability constant, or its square, simplifies to the expression which we see at the top of this slide. So what properties does it have? First of all, if we send D1 to 0, then the exponent goes to 0. And this means that this dangerous term with the exponential disappears. Then before the exponential term, we have a fraction or a multiplicative term. And this prefactor does not depend on D1. It depends on D0, but D0 is kind of not such a strong parameter. It's not so dangerous. And what we also see that this prefactor is proportional to 1/t. So this means that we have two different types of singularities of t. I will discuss this in the block below. What is also now stated implicitly that this estimate holds in the interval from 0 to infinity. In particular, this interval does not depend on any of the parameters which we have, like d0, d1, gamma. Okay. All these three properties we need for a certain application, a certain homogenization limit, which you will see shortly. And in a number of papers, so in all papers which dealt with this problem before, it was not possible to find a result which covers A, B, C, all these three properties at once. Okay, so I mentioned this singularity at small times. And there's a singularity which is linear in 1/t, and a singularity which is exponential in 1/t. And there are indeed examples where this singularity, where 1/t appears in the exponent, indeed occurs. However, if you have a boundedly invertible operator B, this is, for instance, it's true if B is simply the identity, then you have no exponential singularity, but you have still the term 1/t in the control cost or in the observability constant. This is natural because if you want to heat up your room fast, then you have to pay more. Okay, that's natural. Okay, so we have discussed certain features, how the observability constant or the control cost depends on t and some other parameters. So far, the result was written for an operator A, which is non-negative. But if A is merely lower semi-bounded, you can extend a lot of the results, basically by shifting everything by kappa, which is the infimum of the spectrum. I will not go into details about this. You see that the theorem is formulated in a very similar way. In the observability inequality, we keep the old observability constant, but get an extra term in the integral, which is in orange here. And now you can try to derive from this a new control cost, and you see a derivation below. This is an estimate. Okay, I will not go into this, but I just want to point out that it's possible to consider generators of semigroups not only which are non-negative, but also which are lower semi-bounded. And actually, the control cost estimates change, but it's still possible to trace quite effectively how they depend on kappa, the infimum of the spectrum of the generator. Now, what is the connection to uncertainty relations? Well, we had this assumption, which was formulated in terms of spectral projections. This has to be somehow proven so that you can apply this abstract operator theoretic result. And this will be discussed. This is what we will discuss next. So we consider a certain type of domains, which we call generalized rectangle. This could be a rectangle, it could be a half space, a slab, a layer, an octant, a cube, okay? And it's called omega, and it's the Cartesian product of intervals which are open, but may be unbounded. If they are open and non-empty, then they have a certain width, and the minimal width, if you go over all coordinate directions, is g. And then we consider now a self-adjoint operator, Laplace operator, on L2 over this generalized rectangle, and give it some nice self-adjoint boundary conditions. We can also deal with periodic boundary conditions if you have a cube or rectangle. If you have a half space, then of course periodic boundary conditions don't make sense. And in the following, we will consider just a pure Laplacian or a Schrödinger operator where we add bounded, measurable, real potential V. So the multiplication operator to the Laplacian. And in both cases, pure Laplacian or Schrödinger operator, we can consider on L2 of omega the control heat equation, where we have also allowed for heat generation term. Okay. So we have again system 1, what we saw before, but now the generator is a little bit more general. It's still lower semi-bounded. It may be non-negative, but it could also have some negative spectrum. Okay, that's fine. And we consider the problem of controlling the heat equation in finite time t, and we have an initial state w, and the control is a L2 function on the product space. And again, we have the indicator function of omega with intersected with a set S. And the set S is a subset of RD, non-empty, measurable, and we want to know what type of properties should S have such that we are successful in controlling a heat equation. You see that S is not assumed a priori to be a subset of omega. It could live also outside of omega. This is of interest because I want to vary omega along the way. Okay. So, of course, the two properties of sets which we have introduced before, thick sets and equidistributed sets, will play a role here. And I will not repeat the definition, but I will just give you this picture so that you're reminded of it. And the first uncertainty relation which will play a role was one proven for the full space by Kovryshkin in 2001 and by Michaela and myself in 2016 for cubes, but it also holds for slabs and these generalized rectangles. And the statement is the following. Here you consider the pure Laplacian, and you have a subset of RD, which is rho A thick, and you have a generalized rectangle as above, which should be big enough such that it contains the windows generated by the vector A. Okay, so thickness should be somehow compatible with the omega which you're considering here. Then for all psi which are in the range of the Laplacian or the negative Laplacian, so you consider all eigenfunctions up to energy E, except that maybe they're not eigenfunctions, but generalized eigenfunctions because you have absolutely continuous spectrum. You have the following relation between L2 integrals. Okay, so what you are considering is a norm and a semi-norm, and actually you can bound the norm by a semi-norm if you pay a certain constant, and the constant is of the type which we saw before. So actually this abstract assumption 4, which we saw before, is something non-void because here we see an example where this is actually satisfied. Okay. So what does it mean? It means if you make your spectral subset larger and larger by increasing the energy, the constant which you have to pay gets larger and larger, and that's natural because you have more functions psi over which you can vary. Okay, and you can now identify these parameters d0 and d1 which popped up in inequality 4, and d0 is basically inverse of the density to some power. Okay, and d1 is something like the size of the window because A is a vector which determines the size of the window, and you take the L1 norm, and then you get also some mild contribution from rho. Okay. C is a universal constant, so it's maybe something like 300 or 5,000, I don't know, but it doesn't depend on anything, not even on the dimension. So now we can rewrite F using spectral projections. Okay, and then we see that this inequality at the bottom of the page is satisfied, and this is exactly the inequality which we saw as the assumption of the theorem, assumption 4. Okay, so this was a non-empty theorem because the presumption can be satisfied. Okay, now we want to consider more general operators, and now we want to consider Schrödinger operators. So we want to add a potential V. What changes now is that we have to demand more on the set S, namely it should be equidistributed. It should contain open balls. And the statement is that once you fix the dimension, you will find a constant depending only on the dimension, so that for any scale G, for all generalized rectangles omega, and all equidistributed sets S, all energies E, and all bounded potentials and all psi which are in a certain spectral subspace, you have the same inequality as before, but now you have a new constant and different ingredients play a role. First of all, the Schrödinger operator has now a potential. So the differential expression has a variable coefficient term, okay? And this should enter the constant, and you see it entering an exponent as subnorm of v to the power 2/3, okay? We have also the scale G entering. G plays a little bit the role like this window size QA determined by the vector A in the case of thick sets. And if you look at this constant, which is associated to the uncertainty relation, the delta enters in a similar way as the density. So it's kind of the inverse density which plays a role to a certain power. And you see also that if you go up with the energy E, then the constant gets worse with square root of E. This was the same as before. Basically, you should think about it in the following way. If E is the energy, square root of the energy is the size of the momentum, and the absolute value or the norm of the momentum enters in the exponent. And you see a precise way how it depends on the scaling G. G was the size of the lattice in this picture where the equidistributed set was defined. So again, in this situation, it is possible to satisfy this assumption number 4 in our abstract operator theoretic null controllability theorem. So another situation where this is satisfied. Now, this theorem is called scale-free, and it is scale-free in the sense that our Schrödinger operator H is allowed to be defined on any rectangle omega, and omega should be such that it contains a cube of size G. So this was the only relation between G and omega which we needed to assume. This was here at the top of this slide, okay? And if you are imposing this condition, then our results are uniform over the rectangular domain omega, and this is called scale-free. So you could have a sequence of growing cubes and the estimates will be uniform over them. This is what I said before, why I'm choosing the set S as a subset of R, D, and not as a subset of omega, because I want to be able to vary omega. Okay. We want to rewrite this constant CUR in these parameters D0 and D1. And here, just for simplicity, we consider only energies which are above the infimum of the spectrum. This is sufficient for applications. And then you see that this constant UR can be bounded involving D0 and D1, as we had it for our null control theorem, and you identify D0 and D1. Okay. Now, the natural thing is take these two uncertainty relations and combine it with the null control theorem. And if you do this, you get as a first result the following. For the pure Laplacian and omega equals to RD, or finite cube, and then you take a thick set, and if omega is a finite cube, you have to assume that L, the size of the cube omega, is larger than the window size of the thick set. And then if this is true, we have a observability estimate for time t, as we saw it before. So I will not discuss it in detail because this is the third time that we see something like this. But what is of interest, how the observability constant depends on the geometric features of the control set, which we know that it's thick. So we have a rho, the density, and A, the window size. Okay, and we can make it explicit, and we have just some other constants C1 to C4 entering, and these are now universal positive constants, so something like 17, 304, whatever. Okay, and this means that once you are given a thick set, you can also describe how the control cost depends on these geometric parameters. Okay, this is written in the last sentence. Now, let us try to discuss this constant and its dependencies, and we will discuss two features where it's optimal. One of them is the dependence on time, t, and the other one is dependence on the vector a, which describes the window of the thick set S. So first of all, if you look at the dependence of t, you see an exponential blow up for small times, and this indeed occurs at least if S is not the whole set. So if there's some region of omega where you're not acting with your control. These are results by Fernandez and Zuazua and Miller, or actually combining their results and our results, you see that this is sharp. Also, if you look at the appearance of the L1 norm of the window A in the exponent, this is also sharp, which it can be seen if you choose the window size of the thick set to be in all coordinates equal to G, keep the density rho fixed, and then choose a torus where you are considering your problem. So you have a Laplacian with periodic boundary conditions, and then you see in a certain limit that this is the optimal thing, that you cannot have. You will have simply the norm of A squared appearing here. So in these two respects, it's sharp what we derived. And this is of interest also if we want to study the asymptotic behavior of the control cost in a certain homogenization scenario. Recall, S is the set where we act with our control of the heat equation. And now you want to change the following. You say, I will split up the set S to have more and more balls, but they will become smaller so that the density rho remains the same. So we consider now the heat equation with the pure Laplacian on Rd, or a cube with a finite side length, and we fix the density rho. And then for every rho A thick set, and to emphasize the dependence on A, we call it SA, the heat Cauchy problem is null controllable in every time t, and we have a bound on the control cost, which is written here explicitly. And in orange, I've written the term 1 over t appearing in the exponential. So we have an exponential blow up for small times, unless S is the full set, which we'll include now. What we'll do now is we keep R fixed, and we send A, the window size of the thick set, to 0. So what happens? Norm of A simply goes to 0, and this means that the whole exponential term disappears. It just becomes 1. So we get this much nicer constant, which is written in the second block. Right? This is what happens if we send a window size A to 0 while keeping rho constant. So we see that there is a singularity for short times t, but the exponential singularity disappears. It's much milder. The linear singularity is there, and this is sharp when we compare it with the situation that B is equal to the identity operator, or the indicator function on the whole set. Okay, so basically you recover this situation, what happens if you control on the whole set up to certain prefactor, scalar prefactor. Okay, so I move on to a different application of these uncertainty relations. And now we want to do some spectral engineering. So you look at spectral bands of essential spectrum, and you want to perturb them. But it's not so that we want to prove just stability, that if you perturb a little, then the spectrum moves a little. Rather, you want to be able to push the spectrum in a certain direction. And since it's the essential spectrum, things are a little bit more complicated than if you have just matrices and you just do some min-max theorem, okay? And just to get the setting somehow set up, we consider a special case. We have a periodic Schroedinger operator, and this means that you have a periodic potential, and this means that you have a certain periodicity lattice. And we consider now two different rank D lattices with two different cells and two different periodic potentials, bounded and measurable, but with respect to different lattices. If you take one of the potentials and add to the Laplacian, you get a periodic Schrödinger operator, and Floquet theory tells you that you get band spectrum. This is what is written in blue below. You have a direct integral decomposition. You have a fibered Hilbert space. You have a fibered operator using quasi-periodic boundary conditions on the periodicity cell. And since each fiber of the operator has compact resolvent, it has purely discrete spectrum, but actually the full operator has just absolutely continuous spectrum. So you have bands of essential spectrum. Okay, so now we want to add another periodic potential, but with a totally different lattice. And this means that you no longer can apply Floquet theory. But if you had a spectral gap between two bands for the unperturbed operator H0, and you take a very small coupling constant T times the bounded perturbation V1, a band gap will still persist simply by continuity of the perturbation. Okay, so we still can speak about gaps in the spectrum and spectral edges, but let us be more precise and introduce notation to describe this properly. So we start with the resolvent interval of the unperturbed operator H to B, and the edges should be in the spectrum, which is actually the essential spectrum or the AC spectrum, because we have a periodic operator. And now we want to trace how the lower gap edge moves as we switch the coupling T on, the perturbation on. So, and this is done by the function f of t, okay? And if t is equal to 0, it is simply equal to a. This is written down in the picture. So the edge of the spectrum for the unperturbed case. And now to describe the lower edge of the gap ft for switched on perturbation, you take the essential spectrum of h of t and you restrict it to the kind of lower semi-axis, which could go up to A or go up to B. And what you do is actually you go up to B tilde, and B tilde is defined in the following way. You go up to T, but then you have to increase some security distance because B might move down itself. And you don't want to see this part, okay? So you cut off what you see of the essential spectrum at the level B minus modulus T times norm of the perturbation. And what you see there is actually in the essential spectrum, and it's a continuous continuation of F naught. And this is called the lower edge of the gap. Okay, this is how to make this precise. Okay, and this F is actually Lipschitz continuous. So this means if you look at F of t plus epsilon minus F of t, you can bound it up and below by epsilon times the norm of the perturbation. I don't know where this has been proven the first time. I know paper of a relative of mine, who is also called Veselic, and he proved in 2008 this statement somewhere in a long paper. But maybe it was also known before, and it was also discussed nicely in the PhD thesis of Albrecht Seelmann, which is from 2013 or 14 or so. Okay, as in these two sources which I mentioned, you can also find the statement that if your perturbation V0 is non-negative, then the gap edge can only move upwards. You cannot move the gap edge down if you have a positive perturbation. This is quite natural, but you have to prove it. It's not just min-max simply because you have essential spectrum and not discrete eigenvalues. So that's written in red. And now what we want to consider is what is written in magenta. So this means you have a lower bound on the perturbation, which is a functional multiplication operator. And the lower bound is an indicator function of a non-empty periodic open subset of RD. So something like this would be an equidistributed set because it's periodic. And then we want to prove that we don't have only an upper Lipschitz bound, but that we have also a lower Lipschitz bound. So when I speak of a Lipschitz bound, it means that you have kind of a bound on the derivative, and you don't have only an upper bound on the derivative, but also a lower bound, which is positive. This would be this constant C. Okay, so this is our aim. Always when you write down such inequalities, the question is, for what range of T's is this valid? So what is the natural or optimal range of T? Well, we start perturbing a spectral gap. Always when you do spectral perturbation theory, you have to ask, where is the next spectral value? The distance to the next spectral value tells you how far you can perturb it. And here, the gap length plays the role. And of course, you have to divide by the norm of the perturbation, because this is kind of the speed, how fast you eat up your gap length. And now, if you don't assume anything on the sign of the perturbation, you have to divide by 2, because your gap could be eaten up from two sides, from below and from above. And if you assume that V1, the perturbation, is non-negative, you can drop the 2, because your gap, your spectral gap, shrinks just from one side, from below. Now, all what I want to discuss here has been discussed before in the case that the two potentials which we are discussing have a common periodicity. Then you can reduce everything by Floquet theory to fibers of operators, or to fiber operators which have discrete spectrum, and then you just do the usual stuff with perturbation theory as with matrices. Here we cannot do this, and we really have to attack the essential spectrum substantially, directly. Okay, now I will just recall briefly the scale-free unique, the scale-free uncertainty principle. It's the same slide as before, so you can relax. We have this domain which is rectangular. We have this equidistributed set, which means it contains this collection of gray balls. And if I say an equidistributed set, it always has two parameters. G is the spacing of the lattice, delta is the radius of the balls. Okay. And then for a Schrödinger operator with a bounded measurable real valued potential, with nice boundary conditions on this rectangular domain, we have the following scale-free unique continuation principle. And it's the same estimate as we saw before. The only thing what I introduced is what is written in red, which is a supremum over lambda. And this is basically an optimization over shifting the energy. Okay, because if you shift the operator by a global energy shift, you still get the same estimate, and you can you have a family of estimates and you take the best one. Now, we can rewrite this inequality between the L2 norm and the L2 semi-norm restricted to S also as a quadratic form inequality. Let W be a multiplication operator which is lower bounded by the indicator function of S intersected with omega. And then we have the following quadratic form inequality, which tells us that although the multiplication operator W is positive semi-definite, it could have quite a large kernel. If I consider it only on the spectral subspace associated up to the energy E, it becomes positive definite, strictly positive definite. So on this subspace, on this spectral subspace, it has no kernel. Okay, we turn a positive semi-definite operator in a positive definite operator on a subspace. Okay, and of course there's an interplay between the spectral subspace and the shape of the function W. This is all what this is about. Okay. And now we can formulate our first spectral lifting result for Schrödinger operators. Okay, so this is a joint paper with Nakic, Tautenhan, and Teuffer, and there's an appendix by Albrecht Seelmann where he proved a certain min-max principle which we needed. So just as for warm-up, we start what happens below the essential spectrum. There you have only discrete spectrum, so things are easier. Okay, so we choose a certain threshold energy E. This is something like a high energy cutoff. And then we consider any K, which will label the eigenvalues, but we also allow plus infinity. Plus infinity is the bottom of the essential spectrum. Okay. We assume that all eigenvalues which we consider are smaller than E. And then actually we see that we add the perturbation W to the Schrödinger operator. The eigenvalue gets lifted by the constant of the uncertainty relation. Okay, so we have a lifting of eigenvalues and we can quantify it, how big it is, by geometric properties of W. Okay, so this is not so surprising because we are below the bottom of the spectrum and a lot of it works with a min-max principle. However, similar results we can show for something which is not describable by eigenvalues or discrete spectrum, namely we consider a lower edge of a gap in the essential spectrum. So this was something described by the function f before. Again, we have 2 points in the essential spectrum, which are actually gap ends, gap boundaries. We take the length of the gap, divide by the norm of the perturbation, and this is T0. This is our maximal range of the perturbation. And so on the interval from minus T0 to plus T0, we can define these parameterizations of the lower edge of the gap. This is F minus. And in blue, I have immediately written also the same definition for the upper edge. So you can parameterize both of them. This is not surprising, and I will not go through it. Then we have the following upper and lower Lipschitz bounds for the parameterization of the edge. The upper bound is the same as we saw it before. The Lipschitz constant is the norm of the perturbation, that's natural. And we have a lower Lipschitz bound, which is positive, with a positive constant, which is the one from the uncertainty relation. And I have here now different ranges for T and epsilon because T could take on positive and negative values, but basically it means you vary T from minus T0 to plus T0, and depending how the sign is, you have to choose epsilon accordingly. And the same thing holds for F plus, the upper edge of the gap. Okay. So we get a similar result for the perturbation of the essential spectrum. And then also we have results for lifting of eigenvalues inside of gaps of the essential spectrum. For this we need no more notation. So we have now discrete spectrum, but because it's between regions of essential spectrum, things are more difficult. Again, it's so that we will use some operator theory to formulate an abstract results, and then this abstract result will yield the results which we formulated when combined with the uncertainty relation. So the strategy is the same. We have a PDE result. This is the uncertainty relation. You have an operator theoretic results. You combine them and you get something nice for your model. Okay, so a standing assumption here in this part is H0. We have a self-adjoint lower semi-bounded A, and we have a bounded and symmetric operator B. And for the warm-up, again, we consider what happens below the infimum of the essential spectrum. We can enumerate all eigenvalues. Maybe they're finitely many, maybe they're infinitely many. They're all below lambda infinity. And now we fix the k, and this is a coupling constant, or well, a small constant, and we introduce the hypothesis pos E. So pos stands for positivity up to energy E. So for all psi in the range of the spectral projector of the operator A plus B up to energy E, we have a certain positivity of B as a quadratic form, and kappa is kind of the bottom of the spectrum of B on the subspace. And now lemma tells us that if you look at lambda k, you get a lifting of the eigenvalue by kappa. This is quite natural. We just apply the min-max principle. What requires a little bit of thought is when you apply this to k to infinity, where this denotes then the bottom of the infimum of the spectrum. We have to require that lambda k A plus B is below E, because otherwise the assumption pos E would not act here. Okay, so you have to have a sufficiently strong assumption such that it covers the right spectral subspace. Let us prove this statement, and you should focus on the case where k is equal to infinity, because this is the non-trivial part. Okay, since lambda k is below E, we have a positive epsilon 0, which describes the difference. Now, the kth eigenvalue of A plus B can be described by a variational formula. You see the quadratic form psi A psi plus psi B psi. Okay, so what do? Then you take the supremum over all psi, which are normalized, and which are in the range of the spectral projector up to the kth eigenvalue plus some little epsilon. So the epsilon is a little bit too much. You have to get rid of it, and you do it in the way that you take the infimum over all epsilons positive up to epsilon 0. Okay. It's a complicated way. There are simpler formulas, but this complicated formula is what we need. Because we have the assumption pos E, we can bound psi B psi below by kappa. Okay. And now, it just pops up that the rank of the spectral subspace which we have is at least k, because we go up to the kth eigenvalue. Okay. Then this means that for any epsilon, the supremum which we are looking at, okay, can be written in a funny and complicated way, namely by two suprema. First, we split up the spectral subspace in certain subsets L and take supremum over all else, and then we take the supremum over psi in L. So we have divided the supremum procedure in two steps where we take the supremum twice. Why do we do this? Because now one of the suprema we can replace by an infimum, and we get smaller by this, obviously. And then we do the following. This subset L is a subset of a spectral subspace. A spectral subspace is certainly contained in the domain, and the domain does not change by bounded perturbation B. So we can make the infimum smaller by optimizing over a larger set of subspaces, namely L contained in the domain of A. And what we have written here is exactly the kth eigenvalue of A, and we put things together and we are done. So it's a very familiar procedure using the min-max principle, but the difference is that you really have to deal with infinite dimensional subspaces. Okay, it's not finitely dimensional, but you get a flavor of what's going on, what will happen. Okay, Now I mentioned that we can formulate also shifting results for eigenvalues inside gaps of the essential spectrum. The question is how to enumerate the eigenvalues. You can start enumerating them increasingly or decreasingly, but the problem is if you have accumulation points of eigenvalues near the edges of the essential spectrum, then you may have no good choice of enumeration in this way. So what you have to do is the following. You first pick a gamma in the resolvent set, and from this gamma you can start enumerating eigenvalues in one or the other direction, and you get two sequences, possibly infinite ones, and to distinguish them we have arrows. One arrow pointing leftwards if you count in the leftward direction, in decreasing direction, and the other way around. Okay, so we define lambda infinity gamma arrow to the left as the first point in the essential spectrum which is left of gamma. And then you look at all eigenvalues which are between this point of the essential spectrum and gamma, and you order it decreasingly. Okay, and now you want to have some kind of min-max principle for these eigenvalues. And for this, we will use a result by Langer and Strauss, which are dealing with maximal non-positive subspaces. The advantage of maximal non-positive subspaces is that they are more stable than spectral subspaces. If you have a spectral subspace of A and you add a small perturbation B, it's no longer a spectral subspace. But if you have a maximal non-positive subspace under small perturbations, it remains this. Okay? So the statement is the following. For all K and for all any choice of gamma, you have a characterization of the kth eigenvalue lambda as we described it before with a triple variational formula. Okay. Okay, and what is involved is an element, so well, a maximal non-positive subspace M. Then you choose a subspace of this M, L, which has the right dimension. And then you take the supremum over the quadratic form for elements of M, which are orthogonal to L and normalized. Okay. Well, I don't have time really to go through this, but this is a useful formula, and with this we can prove the following theorem. But before this, let us discuss a lemma which formulates what I already said orally. If we have a gamma from the resolvent set and H1, which is a certain smallest condition on B, then the spectral subspace range of the projector A plus B up to energy gamma is still a maximal non-positive subspace for A minus gamma. Okay, it survives the perturbation. And the smallness of B is determined by the size of the spectral gap. So the distance from gamma, the reference point to the spectrum of A. And depending whether B has fixed sign, you can drop a factor 1/2 or not. This is what we discussed before, that a fixed sign enlarges the range of the perturbation. Okay, and now we have the theorem, which says if we have the positivity assumption for B on spectral subspaces, you have the usual lifting of eigenvalues as with the min-max theorem. Okay, and you could even relax it because you just have to look how close is the spectrum to gamma, which is below it. So you have only one-sided perturbation, but I don't want to go into this detail. So anyway, you can prove inside of the gap of the essential spectrum a perturbation and lifting result for discrete eigenvalues in the same way, and it's the same quality as below the essential spectrum. Having this, you can formulate now a result about the movement of edges of the exponential spectrum, now in this abstract setting, but what you will see is the same as you saw before. It's just more general now. So you have a spectral gap in the essential spectrum A to B. A is actually an element of the essential spectrum. You have the positivity up to B of the perturbation B. You define T0 as the natural parameter range until where you can consider the perturbation. You define Ft as the parameterization of the lower gap edge, and then you have this lower and upper Lipschitz bound on F. So you have a positive bound on the derivative and a finite upper bound on the derivative. Okay. Now, if you choose the other sequence of eigenvalues, those eigenvalues which are all above gamma, you get a different sequence with a different notation. Now the arrow is pointing to the right direction, but it's the same as before. It's just the other half of the spectrum on the other side of gamma. So it's all discrete eigenvalues. So what changes? Well, you can prove almost the same thing, but we actually have to use a different min-max principle. In some sense, it's funny that we are not able to treat these two situations symmetrically, but it's just the way it is. So the min-max principle is proven by Albrecht-Seelmann, and it's the following. You pick gamma in the resolvent set, and you have two conditions. One of them tells you that B is in some sense non-negative. This is property 1. And the second property is that the spectral subspaces don't get perturbed too much. Okay. And if this is the case, then you can identify the kth eigenvalue of the operator A restricted to the spectral subspace above gamma by a variational formula. Okay. And K shouldn't be too big. So this is inspired by other min-max principles by Grisema, Lewis, Siedentop, Morozov, and Müller. I will also not go into details about it. I just want to say how you infer property 1, which is kind of a certain smallest condition. So there's this well-known sine 2 theta theorem by Davis and Kahan. And here we just use the version from Albrecht's PhD thesis, where it's possible to bound this by a certain quantity which involves the quotient of the norm of the perturbation B divided by the gap length. And using our assumption H1, one can show that this is smaller than 1/2. Okay. So this is satisfied under our assumption H1, which we imposed. That's fine. Okay, now I come to another application. Now we are also considering essential spectrum of Schrödinger operators, but now they are not periodic or something similar, but they are now random. In fact, the previous theorem also covers random Schrödinger operators, but now we really focus on randomness. And we want to learn something about Anderson localization. So we start with a periodic bounded and measurable potential, V periodic on RD. We add it to the minus Laplacian and get a periodic Schrödinger operator, which is self-adjoint. And then we generate a stochastic field, which will be a bounded measurable random perturbation potential. How do we do this? We have U, a single side potential, which is real valued, bounded, compactly supported, and we shift it around by lattice sides, J, and then we couple it with the random coupling constant alpha J. The alpha J's are bounded random variables, IID, non-trivial, and they have indeed a bounded density G according to which they're distributed. We add this potential V omega to the Schrödinger operator and get a random Schrödinger operator. Okay, actually the subsequent results hold also for more general random Schrödinger operators, but here I just want to focus on this rather simple case. Otherwise, we'll have just too much notation. And here we see what happens if you vary these random coupling constants. You see the cylinders, which should be images of this function, the single side function u, and they have different coupling constants. Therefore, they have different heights. And if you increase all these coupling constants, all these are pushed forward. And in this sense, you get certain positivity for the increments if you choose the change of the coupling constants in the right way. So this will play a role later, but I just wanted to show you a picture how you should imagine this random potential. Now, a few general facts about random Schrödinger operators. Since we assumed that random coupling constants are IID, and since they're attached to lattice points, we get a certain ergodicity property. And this means that there exists a set omega tilde of full measure and a set sigma of the reals, subset sigma of the reals, such that it coincides with the spectrum of the random operator for all omega in omega tilde. So this means almost surely we see the same spectrum, although the operator is the random variable. Okay, so people say the spectrum is non-random. The same holds also for the spectral components. The continuous spectrum, the essential spectrum, the discrete spectrum, the absolutely continuous spectrum, the singular continuous spectrum, and the pure point part of the spectrum. Here, I have to tell you that the pure point part of the spectrum is the closure of the set of eigenvalues. It's not the set of eigenvalues. Okay, we want any spectral part to be a closed set. If you look at individual eigenvalues, you see something totally different. Namely, if you ask for fixed energy E, what is the probability that it happens to be an eigenvalue of the random operator? Then the answer is 0. Okay. This has to do with the fact that the reals contain uncountably many energies. Okay, so this is compatible with the statement before. There's a little bit of a problem here, but it doesn't matter. I can tell you what's on the last line. We can define the spectral distribution function, which measures how dense the spectrum is along the real line. So here we are not asking about the type of the spectrum, but about the quantity or the denseness of the spectrum. Okay. So we consider the spectral resolution of the operator H omega up to energy E. This is a projection operator, and we multiply it with the multiplication operator associated with the unit cube lambda 1. So we multiply two operators, which are both projections. One of them is a projection in momentum space. One of them is a projection in X space. If you multiply them, you get a projection on a bounded set in phase space. Therefore, you can show that it has a finite trace. And if you take the expectation value, this is called spectral distribution function. Okay. Okay, so what's written on the last line of this slide is precisely that we are projecting on a bounded or compact set in phase space. So this is nothing. A few properties of this function. It's a monotone increasing function. And if you look at the points of increase, then this is the support of the associated measure. And this equals sigma, which is the almost sure spectrum. There's a different formula for the spectral distribution function, which uses an exhaustion. So you fix an energy E, and now for each L, you consider the cube of side L. You restrict your operator to this cube with nice boundary condition, and then you consider the spectral projector associated with this operator. This has just discrete eigenvalues, discrete spectrum, so you can take the trace, you take the expectation, you normalize by the volume, and in the limit you get the same expression as before. Actually, because of ergodicity, you can even drop the expectation value here. So due to an ergodic theorem, almost surely the same holds true if you don't have the expectation value. So this is a law of large numbers. People say that the spectral distribution function is self-averaging. It has the self-averaging property. So N of E is also called the integrated density of states, IDS, since it counts the number of quantum states per unit volume up to energy E. So this is a different name. Okay, what will be of interest to us is somehow related to the last part. How does the spectrum as a set change if I add to a periodic Schrödinger operator a random potential? And in order to keep track of the perturbation, we introduced a coupling constant T, which is put in front of the random potential V omega. So now we have H omega T. T is the strength of the perturbation. If you switch on T, the spectrum expands, and this is depicted in the picture below, and some of the previous gaps will survive, some of them will close. Here I have assumed that the density of the coupling constant G has support equal to an interval. If it's not an interval but 5 intervals, say, then this picture could become more complicated because you would get some additional spectral gaps. Therefore, we assume that the range of the random variables is continuous in an interval. So the take-home message is the spectral gaps persist if the coupling constant is small enough. And now, what is the phenomenon of Anderson localization? There, where spectral gaps persist, we assume that we will have localization at spectral edges. Okay, I have forgotten to mark this one blue end also red. Never mind. So you expected where you have, you expected there are small regions, small intervals, which are contained in the spectrum and actually contained in the pure point part of the spectrum and have empty intersection with the continuous spectrum. So here the take-home message is the random perturbation changes the spectral type drastically in certain energy regimes. Okay, I'm not discussing here the details, but what I would like to emphasize is that this is quite well understood for the red interval near or containing the minimum of the spectrum and less so at internal edges. Okay. Now, an important ingredient to understand Anderson localization is the so-called Wegener estimate. So we consider the averaged eigenvalue counting function associated to a cube lambda. So we restrict the random Schrödinger operator to the cube. We count the eigenvalues below energy E. This is the trace of the spectral projector, and we take the expectation value. And the question is this function continuous, Lipschitz continuous, Hölder continuous? And we will discuss two sample results. Before we do this, I just want to recall a picture to make it believable to you that we can expect continuity. So this was this picture which described how the profile of the random potential changes if we increase all coupling constants. Okay, so this means if they conspire in a good way, the coupling constants, they can increase the potential, and this should shift eigenvalues. And if you shift eigenvalues around, then this means that this smears out the spectrum, and smearing out of the spectrum leads to Hölder continuity or to Lipschitz continuity, what we asked about. Okay, two results. The first one considers a periodic Schrödinger operator plus a random perturbation. The random perturbation is as before, and the potential, and this is crucial, U is assumed to be non-negative. Then indeed, we have Lipschitz continuity of the averaged eigenvalue counting function. So the number of eigenvalues, which you see on average between energy E minus epsilon up to E, is proportional to epsilon, the length of the energy interval, and proportional to the size of the system. You have a certain constant CE, which comes from a while bound, so it increases with the energy E. Here, V omega contained a certain type of ergodicity or a periodicity because a fixed potential U was shifted around by vectors in a lattice. This simplifies the analysis, and if you don't have this, you have to apply different tools. Now we consider just for this moment V omega, which is the sum of translates of functions uj multiplied by a coupling constant alpha j, but now the uj don't have to be all of the same shape. They have just to have a uniform upper and lower bound. So this is kind of a non-ergodic random potential. And in several papers, the same bound was proved as we saw before. Okay, so you might wonder, okay, what's now the big difference here? For some reason, people have been interested in these more general models, but more importantly, the tools developed here really have a bearing also for other questions in random Schroedinger operators, and I will present you an example. So the uncertainty relations proved in the paper by Nakic, Teufel, Tautenhahn, and Veselic contributed to the following result. So it's about establishing Anderson localization at spectral edges. We have a random Schrödinger operator as above. We assume that the single side potential has a fixed sign, and we consider a spectral gap from A to B. So this is contained in the resolvent set of the random operator. And the statement is that we have Anderson localization at the upper edge of the gap. So this means in these red regions, okay, there is a small epsilon, so that the interval from B to B plus epsilon is contained in a spectrum, contains only eigenvalues and no continuous spectrum. Okay. This is not completely new. This has been previously known, however, only under heavy assumptions. One of the imposed assumptions concerned the randomness and the properties of the density. I don't want to go into details, but it was a purely mathematical technical assumption, and there's no physical motivation for it. This was done in two papers, one by Barbaroux, Comp, and Hislop, and one by Kier, Stallman, and Stolz. Another one was by myself in 2002, and it assumed regular Fouquet eigenvalues. So Fouquet eigenvalues are eigenvalues of the restricted Schrödinger operator with parameterized by quasi-momentum, and this is associated to the unperturbed periodic operator. And if it has a quadratic dispersion relation near its minimum, then I proved the same result before. And this is actually a natural physical assumption. However, it is hard to prove it. So it's something what you believe that is generically true, but there's no general proof. So this is the reason why this is a very nice result. I like it very much, by Albrecht and Matthias, which shows that under very natural conditions at all spectral edges you have Anderson localization. Okay, so now I'm finished with Schrödinger operators, and now I move on to more general second order elliptic differential operators expressions. We have a fixed dimension. We have lambda subset of Rd, which is either a cube or Rd itself. And there we define a divergence type operators first on smooth functions. A is a matrix which is symmetric, and it's a function which is uniformly elliptic and Lipschitz. These are assumptions which you have seen before, I guess. So I will not spend too much time on it. And this gives rise to an M-sectorial form, and we can define an associated self-adjoint operator by the Friedrichs extension. We can even allow lower order terms, which need not be symmetric. So we get still M sectorial operator, but which is no longer self-adjoint. Okay. And then we have the following sampling theorem. So it's some type of unique continuation result. Well, we define a small radius delta 0, but which is positive and which depends on all the parameters of the model. And then it exists an n depending on the dimension, the Lipschitz constant, and the ellipticity constant, such that for any measurable and bounded potential V on this cube or whole space, for all functions which are in the domain of the operator, and for all functions zeta in L2, which satisfy this relation or eigenvalue inequality or whatever you would call it. Okay, so H is our elliptic operator, V is some auxiliary potential, and zeta is like a small perturbation. And if you choose any delta which is smaller than delta 0, and then you consider an equidistributed set, you can compare the norm of psi on the whole domain lambda with the norm on the equidistributed set if you add the norm of this perturbation zeta. Okay, why is this perturbation zeta useful? It's useful if you consider not pure eigenfunctions, but approximate eigenfunctions, because approximate eigenfunction means it's an eigenfunction up to an error, and the error you put into the zeta. And again, you have here a constant coming from a scale-free unique continuation estimate, which is very similar to the one which we saw before. But now we have B and C, the coefficients functions popping up. And of course, the constant n does not depend only on the dimension, but also on the ellipticity and Lipschitz properties of the matrix function A. And unfortunately, it's very hard to make this dependence explicit. Okay, so this is a sampling theorem proven by Martin Tautenhahn and myself. And how can you use it? So how can you use this freedom which you have in this zeta? And this is applied in the following thing. So this is an uncertainty relation for arbitrary positioned short intervals, short energy intervals. So we have a delta from 0 to delta 0. This defines a radius, and with this we consider a 1 delta equidistributed set S. We fix an energy E. This will be the middle of the energy interval, and we have an n as in the last theorem, and we define a kappa, which is similar to the constant of the uncertainty relation which we saw before. And then we have, in the sense of quadratic forms, the following. The characteristic function of the set S is by itself a non-negative operator, but if you restrict it on the spectral projection on the small energy interval E, it becomes a positive definite operator, and you can quantify how positive it is. Okay, a similar thing we saw before. Here it's essential that you choose the energy interval small enough, because this allows you to treat a linear combination of eigenfunctions by considering this eigenvalue inequality. Nearby eigenvalues give rise to linear combinations of eigenfunctions, which looks very close as an eigenfunctions on the remainder is put into zeta. Both of these theorems, I should say, are inspired by a result by Abel Klein, which was quoted on some pages before, but not for these models, for other models. Okay, so you see something similar as has been proven for Schrödinger operators can also be proven for these more general elliptic second order differential operators. However, there are also differences. So what is the difference between this case and the case of Schrödinger operators? What I suppressed in the last two theorems, we have to impose a certain technical condition which allows us to extend solutions to larger domains, and the condition concerns the matrix functions, and you only need it if lambda is a finite cube. And it describes the behavior of the matrix function A near its boundary. Never mind, I don't want to discuss it. I just want to say there is some technical thing. The uncertainty relation which we saw in the last theorem holds only for psi element in the range of the spectral projection on a very short energy interval. If we consider instead Schrödinger operators, then I could be an arbitrary bounded interval. Of course, the constant will depend on I, but you have no restriction on the length of it. The longer I is, the worse will be the constant, but any choice is legitimate. This limitation can be removed, but it's quite a bit of work and we are working on it. Secondly, in the Schrödinger case, the constant n appearing in the exponent depends only on the dimension. So it's quite universal. Once you fix the dimension, it's fixed. Here, it depends also in the behavior of the coefficients of the matrix A, on the Lipschitz constant and on the ellipticity constant. Especially the dependence on the Lipschitz constant is not nice. You would like to remove it. So it's hard to make it explicit. So let's think of it that you have a matrix A which corresponds to some homogenization problem. Then you would like to introduce oscillations which become more rapid, and then your Lipschitz constant will explode. And then probably it means that your bounds on the constant n will become useless. So this would be a problem. There is some good news about this. So I don't know much about homogenization, but maybe there could be some use of our results to it. I'll just repeat in the first two items the problem which we face here. Unlike in the Schrödinger case, the constant n depends on the ellipticity and Lipschitz constant. And if you treat some homogenization problem, the Lipschitz constant will explode due to oscillations. However, the good news is there's a certain regime where you can get rid of this dependence, namely if you consider a short interval containing the bottom of the spectrum. So you're near the bottom of the spectrum, then you get this uncertainty relation, as we saw it before, with the constant kappa, which is independent of the Lipschitz constant. So this means that even high frequency oscillations can be accommodated. You can pass to a limit, and even though the frequencies increase, you still get the same constant. But as far as I can see, this is only of interest if you consider a homogenization problem on an unbounded domain, where it's not possible to isolate the ground state. Because if you have a bounded domain and an isolated ground state energy with a gap above this, you can treat, I think, all these problems in a different way. But in the case of unbounded domains, there might be something interesting in it. Okay, so I hope that you are not fallen asleep so that you can see the last slide, where I thank you all for your attention.